PhET simulation that simulates the photoelectric effect. And there's a lot of things that this simulation does that would be very difficult for us to accomplish in class. And so we're going to use the simulation to try and better understand the photoelectric effect. And so the first thing that I'd like to point out is just some of the things that I can vary in this simulation. So for starters, at the bottom there's a battery, and right now it's at 0 volts. And I can change that to have some positive voltage. Apparently I can get to be as big as 8 volts. Or I can make the voltage negative, which in this simulation means flipping the battery around the other way. And you should be able to see that, well, it's difficult to see, but on the plates that are here, this plate right now is positively charged, and this plate is negatively charged. So this is the positive end of the battery and the negative end of the battery. And so when I flip it the other way, now this plate is positively charged and this plate is negatively charged. So I'll set the voltage of the battery back to 0. Up here I can also change the frequency of the light. You can see that there's a wide range of wavelengths that are shown here. All the visible wavelengths, infrared, and then ultraviolet. And so that is changing the frequency of the light that is coming out of this lamp. I can also change the intensity of the light. And so right now the intensity of the light is 0, so there's actually nothing coming out. And if I raise the intensity of the light, then you would see light coming out of that lamp. And so starting off with the intensity at 0, that means there's no light coming off of the lamp, and so there shouldn't be any electrons that are coming off of the plate, right? Because there's no light incident on the lamp. But the moment I turn up the intensity, then electrons can be ejected by electrons from this metal plate can be ejected by this light, and we're seeing some of those electrons come off. Now, because the voltage is at 0, there's effectively not even a battery as part of this circuit. Neither of those plates are charged. So this simulation shows a bunch of electrons coming off, but without a battery, really, when those electrons come off, they would just go in random directions. Some of them should be going up and down and straight across and in a bunch of random directions. The moment I produce a voltage down here, you can see the electrons maybe sped up a little bit there. Now there's charges on these plates. This one is negatively charged and this one's positively charged. So when the light kicks off for the same intensity and the same frequency, when the light kicks off an electron, it now, due to the fact that there is an electric field between those two plates, is going to accelerate towards the positive plate. It's repelled by the negative plate and attracted to the positive plate. And if I made the voltage even greater, hopefully you can see that the electrons move even more quickly across there. For the same intensity and the same frequency, if I reverse the polarity of the battery, then I reverse the polarity of the charge on the two plates. So if you make this a small negative number, then what you should see is that there's a voltage where those electrons don't quite make it across to the other plate. If I lower it a little bit, then the electrons are able to get even a little bit further, and you can see that some of the electrons are making it. Apparently not enough for there to be a very strong current here because it says 0. If I make it even less, then maybe some more electrons can make it across, but some of those electrons aren't quite making it across. As I increase the voltage, none of these electrons that come off are going to be able to make it. And so one of the things that we learn about the photoelectric effect is that if for this particular voltage, which is either at or beyond the stopping voltage of for the current intensity and frequency of the light, if I want those electrons to be able to make it across the separation between the two plates, I've got to play with the frequency or the intensity. And so one of the things that I can do is increase in intensity. So I'm going to increase the intensity of the light. And what I observe between the high intensity and the low intensity is that for the very high intensity, so now I'm at 100%, it seems like there's lots of electrons that are coming off. If I go back down to like 8%, there's not nearly as many electrons that are coming off. And so our initial, sort of classical understanding of how the intensity should affect what's happening to the electrons is we say, well, I have a much more intense beam. That should give the electrons a lot more energy and allow them to travel between these two plates. But what actually happens is for the much more intense beam, the electrons don't have any more energy than what they had originally. There's just a lot more electrons that are coming off. If I want any of these electrons to make it across, the thing that I have to manipulate is not the intensity, but the frequency. So let's lower the intensity back down. And now let's start to increase the frequency. So by doing that, I'm decreasing the wavelength. And as I do this, you should start to see that the electrons are going further and further to the right. And eventually, there's a bunch of electrons that are making it across, and there's a current produced in the wire. And so our original understanding was that the intensity would give the electrons more energy, but the frequency wouldn't matter. But what we see with the photoelectric effect is that actually the intensity doesn't determine how much energy the electrons have, it just determines how many electrons get ejected. And the frequency is what determines how much energy those electrons have. In fact, if I keep this constant intensity and I turn the frequency all the way up, which is making the wavelength as small as possible, hopefully you can see that those electrons move quite fast. And as I lower the frequency, it's pretty easy to see that the electrons moving from left to right don't move as fast. In fact, they move so slow that they're stopped by the electric field between the two plates in reverse direction. So there's lots of things that we could play with here. We could look at the intensity a little bit more and play around with the frequency a little bit more. But they also show different graphs here. One of the graphs that they show is the current versus the voltage. And so one of the things that I want to do is I want to set up the experiment so that way there are some electrons that are making it across. So I don't really care that much about the intensity. So I'll just set that at some middle value of about 40%. And I want to make sure that the voltage isn't so high so that it's not super difficult for the electrons to get across. And then I want to increase the intensity until there's a decent number of electrons that are traveling across. So here we see that there's lots of electrons that are traveling across, producing a current in the wire, and we see that current measured down here. And now what I want to do is I want to take my voltage and I want to go through a wide range of voltages and see what the current as a function of voltage looks like. So let's do that. I'm going to first take it to the right, and then I'm going to come back to the left, and you should be looking at the graph on the right. So what we see is that at about 0 volts there is a current that's produced, and that's because as the electrons are ejected from the metal, they're sort of randomly sent off, and some of those are going to make their way to the other plate. The current increases a little bit. If I zoom in on the graph, maybe we can see it, maybe we can't, but the current will increase a little bit as the voltage increases. But beyond about 1 volt, the voltage is going to be constant because as long as this light is able to eject some of the electrons, they're able to make it across there no problem, independent of what that voltage is. If I make the voltage negative, then the current starts to decrease because the electrons are moving in a direction that is opposite the direction they should be moving according to the electric field, and so the electric field opposes their motion, and they start to slow down, so not as many electrons are able to make it across. As I keep increasing it, we'll get to a point right about there where the current becomes zero, and I see that in the graph, and this would be approximately the stopping voltage for this intensity and frequency of the light. So at this voltage, none of the electrons are making it across. And in my graph, I should expect that for any voltage bigger than that, the currents are all going to be zero. So if I increase the current anymore, we should see that little red dot moving along and keeping the current at zero. The next graph that is shown there is current as a function of intensity. Earlier I showed you, or I described to you that the intensity is just describing like how much light is hitting the thing. It doesn't give the electrons any more energy, it just describes how much light is hitting the plate. And I can show that here. Instead of showing the intensity as like a beam of light that's, very intense or less intense, it looks better if I have the color very intense or less intense. I can show the photons instead. And so Einstein theorizes that the intensity of the light or light are little individual chunks, little packets, little quanta that are, we know as photons. And if I increase the intensity of the light, what I'm really doing is just sending more packets of light, more photons toward the plate. And if I decrease the intensity of the light, then I'm just sending fewer photons. And so as I increase the intensity, so if I decrease the voltage, actually if I just reverse the polarity, for a constant frequency, if I start to increase the intensity of the light, I'm sending more photons to the plate per unit time. And so we should expect that more electrons make it to the plate. And that's what we see in the graph of current versus intensity. For higher intensity, the current is higher. That doesn't mean that the electrons have any more energy. Still, the intensity is not what determines the energy of the electrons. What determines the energy of the electrons is determined by the frequency of the light. But the intensity increasing will mean that the current will increase because it's going to eject more electrons. And that's what I see in the graph. The last graph is a graph of energy versus frequency. And so we know that there is a minimum frequency that has to exist in order for those electrons to make it across, because the frequency is what determines the energy. Even for some reasonable polarity of the voltage like this, where the electrons want to get away from this plate and move towards this positive plate, if I make the wavelength very, very big, and therefore the frequency is very, very low. If you look at the graph down here, the frequency is very low down here. If I make it even lower, you can see this blue dot moving maybe even further to the left a little bit. With the frequency very low, it does not matter what the intensity is of this beam of light. The frequency is so low that the electrons do not have enough energy to be ejected from this plate and move across. And the reason for that is because this plate, which is apparently made out of sodium, and I can change the plate to zinc or copper or platinum or calcium or some unknown material. And you can see that the surface of this plate is changing as I go from sodium to calcium. It's changing in color to indicate that the surface of that plate is made of some different material. Those different materials require a certain amount of work in order for you to eject their electrons. And so in order for sodium's electrons to be ejected, I have to have enough energy given to those electrons. And the energy that's given to those electrons is not determined by the intensity of that beam, it is determined by the frequency of that beam. And so if the frequency is too low, if the wavelength is too long, those electrons will not be given enough energy and they will not be ejected. As I start to increase the frequency, and so we're looking here as I'm increasing the frequency, but we're also looking down here as I am changing the frequency in the graph. As I increase the frequency, there's going to be a point at which, for sodium, I have done enough work, these photons have done enough work in order to eject those electrons. And you see in the graph that the electron energy was enough in order to be ejected, and we start to see the energy increase on the vertical axis here. And so as I go, there should be a linear graph there. And the slope of this energy versus frequency graph, if you look at the equation for the photoelectric effect, should be Planck's constant. And the x-axis represents that minimum frequency at which the electrons can get ejected. And I don't know the relative work functions, the amount of work that you need to do in order to eject electrons for sodium, zinc, copper, and platinum, but I bet that the minimum frequency at which electrons get ejected for those different materials are not the same. And so let's figure out an approximate value for the wavelength or the frequency that I need to do this for zinc. It looks like, or sorry, for sodium. Right now I have sodium on the plate, and it looks like right around here, about 500 nanometers or so for the wavelength, which corresponds to about 0.7 times 10 to the 15 hertz for the frequency. Electrons are getting emitted. And now let's switch over to zinc. And immediately we see that the surface has changed, and this frequency, this wavelength, is not allowing any electrons to go. So I'm going to have to increase the frequency in order to eject the electrons. I don't know where that's going to happen. It happens much later, right? And so I can look at this graph and see that the frequency needed is much higher. And so if I need a greater frequency of light in order to eject the electrons and give them some energy, then what that must mean is that because the frequency is higher, that zinc has a higher work function than sodium does. It requires more energy, more work in order to eject the electrons. If I go to copper, it looks like it's in a similar place, right? Between the 0.75 and 1.5. For zinc, it was between the 7.5 and 1.5. Okay, so different materials have different work functions. And so overall, I think there's a lot that we can play around here, and you do need to know what the graphs look like and whatnot. But the big takeaways is that this simulation, while it's not proof, it does help you visualize that the intensity of the light is, can be interpreted as the number of packets or the number of quanta or the number of photons that are hitting the plate per unit time. So higher intensity means more photons, lower intensity means fewer photons. If I have a higher intensity, it means more electrons get ejected because there's more photons, but those electrons don't have any more energy than what they have at lower intensity, which is a strange thing that occurs. And the frequency is what determines the energy of those electrons. When I have a frequency that's too low, then the electrons don't even have enough energy to get ejected. As I increase the frequency, the electrons get more and more energy. Okay, and we can see that as the electrons get ejected and are able to make it across, or able to make it across at even higher speeds. There's also some things that aren't necessarily the photoelectric effect, but are experimental things that we take away from this, and that is what's going on with the polarity of the two plates, whether they're positive or negative, how easy it is for the electrons to go across when it has one polarity versus the other polarity, what's happening with the electric field in between those two plates, and why some of those electrons are stopping and going back the other way due to the difference in the electric potential energy between the two plates and them not having enough kinetic energy. So I realize that I've babbled a little bit, and it's a little bit to go through all of this at once, but hopefully you're able to take some of those things away And hopefully that looking at the simulation a little bit helps you understand the photoelectric effect a little bit better.